All right, good afternoon, everyone. I just picked on David's talk, and he has so much to talk about, so I'm going to skip all the announcements and go straight to introduction so he has more time to talk about the amazing things he has to talk. So I'm Pavlos Protopavas. I'm the Scientific Program Director for the Institute for Applied Computation Science, and I'll introduce the speaker today. So David Lloyd Sondak, if you know someone very well, you use his middle name too. Most of you know him. He's a great lecturer here at IACS. So he graduated in mechanical engineering in 2008 from Lehigh University. And then he did a PhD at RPI at aeronautic engineering. He kept going on to engineering path. And then he moved to University of Wisconsin, the math department. Things start getting better there for postdoc. And then to UT Austin in the ICES. He didn't like the acronyms there, so he decided to change them a little bit. So he decided to come to IACS, close. The funny story is that when David applied, I look at his resume, and then I talked to him on the phone, and I said, this is the guy we want to come here. He seems like a nice guy, great lecturer, great researcher. He must be a steal. So I so happened to have a conference in Austin too, so I went there. My goal was to go and get him. I took him out for beer, a couple of beers, and that did it. So if you want anything from David, there's two things he loves, beer and dogs. So if you give him a dog, something with a dog and beer, he can do anything you want. So David now is a lecturer here at the ICS. He's teaching the CS207. He's gonna be teaching extreme computing in the spring. He's co-teach CS205, the parallel programming, and he's also helped with the capstone, and he's going to be teaching a mini capstone in the spring. So he's teaching a lot. He's a great lecturer. He's a great mentor. Students that interacted with him, they love him. They always go to his office for advice and mentoring, and also about the class. So please help me welcome David.
Okay, thanks, Pavlos. So I'm David, and today I'm going to talk about fluid mechanics with turbulence, reduced models, and machine learning. And each one of those words could be a textbook in itself, so we're not going to go too deep into all of these topics. I want to first begin just by acknowledging various people who I've worked with. I'm going to show some pictures, and various people have been involved with making these pictures for the research. In particular, today I'm going to talk about the work that one of our master students, Ray Fung, has been working on in collaboration with me and Pavlos and Saro Suchi. And that'll come at the end of the talk once we kind of set everything up. So here's the plan for today. I'm going to begin with a kind of a very broad introduction to give some intuition into what fluids are, why we care about them, some of the essential features, some numerical stuff to get some intuition for numerics, and then a little bit about some intuition for multiscale behavior, because eventually I'm going to talk about turbulence, which is one of my first loves. And I won't go too deep into turbulence either. I'll just motivate the kind of the cornerstone ideas in turbulence. And then I'll segue into talking about reduced models for turbulence, in particular RANS type models. And then these are very old models that have been studied for a long time. And then I'll get into some machine learning ideas that have been applied to some of these models before ending with some conclusions and some of the directions we're thinking about going. All right, so why do we care about fluids? Well, because they're everywhere. And these problems that I've highlighted on this slide are sort of our motivation and inspiration for studying these things. I'm not going to talk about solar dynamics in this talk, but it would be really cool to simulate a sun, wouldn't it? And in fact, that's actually an important problem, because as we humans become spacefaring creatures, which we're trying to do, the sun sets the weather for the entire solar system. So when we go out there, we better be able to predict the weather, right? And that's tightly coupled to what the sun is doing. Really complex object, of course, very turbulent in there, and it's a plasma. On the upper right corner, we have an example from geophysics, where I'm going to talk a little bit more about this in a second, but the center of the Earth is really, really hot, and the surface of the Earth is not so hot. And there's this big temperature gradient that can drive geophysical processes, like plate tectonics and stuff like that. This is going to blow your mind, but rock is a fluid on geologic timescales. So And actually, the center of the Earth is like a liquid molten core, which is turbulent, and then that is thought to give rise to the Earth's magnetic field, which protects us from the sun, right? So everything's connected, and it's all because of fluids. Here is a cauldron of liquid metal on Earth. You don't get to say cauldron too much in scientific talks these days. So that's what that is. And that's sort of like for a steel manufacturing process, right? And we need to be able to create these things. So being able to predict the behavior of this type of a fluid in complex geometries for real engineering applications is important. So all of these things involve fluids that conduct electricity, because that's sort of where I kind of entered the stage with magnetohydrodynamics and this kind of thing. So I thought I would put another picture up that doesn't have electrically conducting fluids, a nice cloud. This is atmospheric sciences. Also, very complicated object there, that cloud. Not even just strictly hydrodynamics. You have multi-phase flows, all sorts of things going on. But actually, the dynamics of the clouds are an active area of research that people are trying to understand, also tightly coupled with fluids and turbulence. I'll also mention here, although it's not really in my research window, but there's also fluids and biological flows, right? So you might want to predict like the pressure on your arteries due to your blood or something like that. So there's all sorts of fluids, no matter what, you can't get away from them. So here's a motivation for a very famous problem called thermal convection in the geodynamo. So thermal convection drives most fluid flows in the universe. And I met someone once who said it is the most important force in the universe, but I'm stopping short of saying that. I just want to show you why and how it's involved in so many different things. So here's a paradigmatic kind of canonical flow. We have fluid that's confined between two plates, two parallel plates. The bottom plate is hot, the top plate is cold. And it's in a gravitational field. And this is an unstable configuration. So the cold fluid wants to fall, and the hot fluid wants to rise, like a hot air balloon, right? And then suddenly the flow starts to happen in here. You get these really cool structures. And I'll show you some videos of that in a minute. So I have this really cool video that some of you, I think I've shown it to you before. This is, I did not make this movie. This is a cutaway of the Earth. And you have the hot molten core in here. And then you have some rock, like the mantle, and the surface of the Earth is cold. So that's basically the situation I just showed you, right? You have hot on the bottom, cold on the top. And if you let this thing go, you get this really beautiful plume. I'm pretty sure this isn't from a real simulation. I think this is an artistic rendering. But the plume sort of scrapes along the surface of the Earth and causes the surface of the Earth to move. And this is thought to give rise to, these subduction zones and all sorts of plate tectonics and fancy things like that. And it continues on, right? I think the video, I'm not going to show you the whole minute, because I think it starts talking about volcanoes and stuff after that, which also has really cool fluids in it, but not going down that route today. So, all right, so that's showing you that rock on geologic timescales could be a fluid. That's sort of relating to this thermal convection problem. Here's another picture of the geodynamo. I alluded to it earlier, where you have a liquid core, it's like molten liquid core, and that core is in motion because of the extreme temperature differences between the center of the Earth and the outer core here, and you get these turbulent motions, which are thought to give rise to the Earth's magnetic field. That's called the geodynamo. And without that, we would not be alive on Earth, because the sun would just totally destroy us all, right? All right, so that's some case for why thermal convection is prevalent and important, and why you might want to study it. Now, how do you study this kind of thing? Well, one of the things that are in common here is that there's a lot of heat that's being transported around. And so you might want to be able to characterize how the heat is being transported, because that might be able to predict the rising of those plumes and the forces on the Earth and stuff like that. So here's a draft simplification of this. This is the advection diffusion equation for the temperature field, where we're going to say T is the temperature, that's carrying the heat somehow. And on the left you have the rate of change of the temperature, and that's driven by convection, where U here is a velocity field. So this is like the heat's being spread around and carried around by the velocity field. And on the far right, we have the conduction term, which is just your run-of-the-mill heat conduction, where if you put your metal spoon into a cup of tea, come back later and the whole spoon is hot, even though the tip didn't touch the tea, right? The heat conducted through the thing. All right, so studying this equation is not as easy as it looks, it turns out, because you have to figure out what to do for the velocity field. And that's going to be the subject of pretty much the rest of this talk in a little while. How do you determine the velocity field? That comes from the fluids equations. But if you can do that, I'm going to show you a little video here. So here's the configuration. Wait, don't look at that yet. Okay. All right. Why is it not rewinding? Well, here's what it does. So the fluid all of a sudden starts to move. The bottom plate here is hot. This is the bottom plate, and this is the top plate, which is cold. That was the configuration that I showed you on that slide. And you get these are temperature. So the red is hot, the blue is cold, and the really light colors are basically medium temperature. Okay? And so what happens is the heat is getting thrown up from the bottom, and it's mixing with the cool temperature, and you get these really cool structures, which some of you might be able to see, like these plumes that are shooting up through the middle. And in here, if you look closely, you see some beautiful, delicate spiraling going on. And so this simulation was done relatively recently. And I can give you details if you want sometime. I'm not going to get into that now. So that's the kind of dynamics that you can get just from solving this equation with when you specify it coupled to a velocity field. All right. So if you ignore this middle term, the convection term, then this gives rise to the usual heat conduction equation. And I'm going to use the heat conduction equation to motivate some of the ideas that we're going to use later on when we talk about numerics. Because the middle term is kind of a pain, right? It's nonlinear, and we don't really know how to handle it. So let's just throw it away, and we can consider PDEs 101. So if I look at, I want to determine what the heat conduction is in this bar, right? So that means I want to see how heat is being conducted as a function of space and time. It's a one-dimensional configuration. On the left, x is equal to 0. On the right, x is equal to L. The temperature on the left is specified to be 0, and the temperature on the right is specified to be 0. Those are your boundary conditions. Okay, this is like what you teach in the first day of PDEs class. The temperature evolves according to this PDE, the heat conduction equation, in one dimension inside the center of this bar. So if you could solve that thing, then you would know the temperature everywhere inside this bar for all time and space. And you have to specify some initial temperature distribution, right? Because you need to know what the temperature looks like initially. Maybe it's a constant, maybe it's a nice little sine wave, what have you. That's the f of x. So you know how the temperature is initially distributed in this bar. All right, so the way you go about this, I'm not going to do the full derivation, just so you know. People usually set up this so that you have the temperature is split into a x part times a t part, and you need to find theta of x and y of t. You turn the crank, and you end up getting this kind of a solution. The temperature is this infinite sum of sines in x and exponentials in time. All right, so one thing I want to point out here, it's very convenient to have an analytical solution because, as you can see, in time, this is exponential to some negative power. As time goes on, this thing is decaying, so we see that the temperature eventually settles out to 0, right? All the heat got dissipated through the boundaries here. The thing I actually want to focus on, though, is the sine term, because this is going to give us into numerics and multiscale stuff. So the sine term here, it's saying that whatever the temperature distribution is in x, we can represent that as a whole bunch of sines, right? That's like a Fourier sine series. Most of you have probably come across that at some point in your life. And here we have this mode n. So that's basically setting the frequency of the sine. So the solution in x is a whole bunch of sine frequencies, slowly moving frequencies and really fast oscillating frequencies. All right, so what does that mean? So let me show you a little picture here. This is a kind of an ugly temperature distribution. That's the initial temperature distribution in this bar, for example. And it's a third order polynomial in x times some weird exponential in x times some sines and cosines. And this is what it looks like, this kind of wavy structure. And the reason I chose this is because I got these little blips here, which I call like small scales, fast, high frequency modes, and this little inflection point. And we have these kind of slower scales as well, these big humps. Now, if I try and represent this thing in a sine series with just 5 terms, I get this dashed red line, and we see that it's just junk, right? That it basically has none of the dynamics of the temperature field in it. If I try to use 10 terms, I get in closer, right? You see that we're starting to get some of the bigger scales, but it's just kind of jumping over the really interesting dynamics, like the little, not interesting necessarily, but the smaller scale dynamics. And then when you get to 25 modes, you see that there's no difference between the temperature field, the exact one, and the actual approximation. So what's interesting about this is that you might say, well, I still had to use 25 sine waves, but 25 is a pretty big reduction from infinity, isn't it? And that's, I think we can all agree with that. And so I'm trying to use this as a motivation to show you like an idea of a reduced model. That if somehow you have all these crazy scales going on in your actual simulation, what you can do is you can come up with reduced systems that are much easier to handle, right? So going from infinite number of degrees of freedom to just 25, something like that. So, okay, so that was a fun little exercise. We just did a 1D PDE, and we feel really confident that we got to what Euler knew in the 1700s. But as we continue to explore these mathematical models, we find out that some PDEs just can't be solved analytically. In particular, that I'm going to talk about today is the Navier-Stokes equations from fluid mechanics. There's a beautiful set of equations from general relativity that in general can't be solved analytically. And just to show you, I love showing people this. Here's a list of nonlinear PDEs on Wikipedia, organized alphabetically for you, including Greek letters. And each one of these could make your entire career, right? Some of them have been solved analytically, I should say, but there's lots of them. So here's the Navier-Stokes equations, our good friends in here, but they're all over the place. And these come from examples across physics, not just in fluid mechanics. All right, so even when we can solve the equations analytically, sometimes the expressions are just hard to evaluate, so we don't really want to solve them analytically. They might be infinite series. We might have special functions in there, like Bessel functions, which are cool, but they're kind of expensive to evaluate on a computer. And sometimes we don't even know the equations. And so this might be when we start resorting to statistical techniques and data analysis. Right? This might be like financial models or social systems, this kind of thing. So what I'm going to talk about mainly is the need for numerics. What are they? Well, they're techniques and strategies for solving problems on computers. That's about the most least informative definition you could ever hear, but I'm going to talk a little bit about what that means. Okay, so I'm done showing you extra slides, so I'm actually going to move over here because it's better. All right, so I'm going to review some popular spatial discretizations that you may have encountered in your life. I'm going to start with some spatial discretizations. So remember that temperature field evolves as a function of x and as a function of time. And so we need to discretize the whole thing in x, and we have to somehow find a discretization in time. So here are four popular ones. Your finite differences, which are sort of what you learn in numerics 101, where you're just going to represent the derivative as a finite difference between the solution and on some grid. There's the finite volume method, finite elements, which I've spent quite a lot of time thinking about. This is where you're going to represent your solution. You're going to break your grid into a bunch of finite elements, and you're going to represent the solution over each element. Basically, it comes to writing the solution as a linear combination of some basis functions, where these are polynomials, low-order polynomials. And then you have the beautiful Fourier spectral method, which is inspired by saying that, well, this is just sines and cosines, so we're just going to represent our solution as a Fourier series. And then, maybe we don't have all the Fourier modes and we can truncate them, or maybe we don't even need to do that, right? Okay. So here's an example using finite differences, in case you haven't seen it before. Suppose you want to discretize the 1D Poisson equation. Here it is. We're going to try and solve for y as a function of x. F of x here is just some forcing function. And we have some boundary conditions at 0 and L. So what you do is you introduce a grid spacing delta x so that each point in x is represented as j delta x. So if j is equal to 0, then x is equal to 0. And if j is equal to n, then you're at L. And so if you choose a really small delta x, then your n has to be really, really big, right? You need a lot of points. And that can be quite expensive to deal with numerically. Nevertheless, we proceed. We introduce an approximation for the second derivative here. This is a finite difference approximation, second order finite difference approximation. And what I want to point out here is that you're going to try and find the yj's for all the j's, and you're using information for the left, so in front of and behind that point, right? You could use bigger stencils as well, of course. And then once you go ahead through this, you get a solution at point j is determined basically from this matrix equation. A times y is equal to delta x squared times f. And if you can invert that system or solve it in some convenient way, then you're all set. In this particular example, it's very cheap to solve this thing. You could do it in 8 seconds, or actually, hopefully less than 8 seconds. It should be microseconds. And but of course, you could imagine if your n is like trillions or quintillions, in size, then this matrix is really big. You might not even be able to fit it in memory on a computer. And the algorithms used to solve this system, even if they're efficient, it might be challenging to access that, to deal with that. All right. We also have to discretize things in time. And there's lots of different ways of doing this, because people have thought about this for many, many centuries now. For several centuries, not many, many. Backward differentiation formulas, these would be things like the backward Euler method, Runge-Kutta methods, which are kind of even hotter these days than they have been for a little while. People are kind of looking at these in real detail now. Symplectic integrators, which try and preserve important things like conservation of energy through your numerical method. So here's an example of backward Euler method. You got your nice friendly ODE. dy dt is equal to f of y and t. F is some right-hand side. It might be a function of y and time. And you have some initial condition. So from some initial state, you're just going to let the thing go, and you're going to see what the trajectory looks like at some later time. So we're going to introduce a time step, delta t, so that t sub n is n delta t. That looks familiar because it looks the same as what we did for the finite difference. When n is equal to 0, t is 0. And then depending on what your final time is, you have some number of time steps. We're going to use a first order accurate finite difference where we're going to say that we're going to try and find y at n plus 1, which is the next time. And we're going to use information from yn to do that. Right? So yn plus 1 minus yn over delta t is your dy dt. And then you plug this thing in, and you get this equation, which is a nonlinear algebraic equation that has to be solved for y at n plus 1. OK, and then you could probably use your favorite thing in the world, which is hopefully Newton's method, to solve that and get some nice results. One thing I want to point out here, that there's a difference between this kind of finite difference and the spatial discretization, is that this type of finite difference method that I'm showing you here is causal in nature. Right? So when people develop time integrators, they try and use information from the past, because as far as we know, future events are not influencing us right now. Right? It sounds funny, but probably that's not the case. And so we don't want to use a time at, in front of where we are right now. So we're actually just going to use time from behind. You can use as much time as you want from history, but you can't use time in front. All right, so that's causality. All right. So I'm going to give a little cartoon for numerical discretization, try and hammer home some of the ideas here. So here's our favorite function for today, what was the temperature field, but now it's not labeled, so it can just be whatever you want it to be. And it has some little squiggles and some big squiggles, right? And it's on a domain between 0 and L. You introduce a grid. So I'm going to try and find the solution at point L over 4 and 3L over 4. And if let my numerical method run and I get this kind of solution, and we see that it's complete trash, right? It's just not, it doesn't give you anything. But it illustrates one point here, which is that in between the grid points, right, between this L over 4 and this 0, you have lots of dynamics. And the things that are going on between the grid are what we call the subgrid effects. Right? These are things that are not represented by the grid. And so you get little blips. And in this case, it's such a bad discretization, you're not even capturing, anything. But this is just for fun. So we increase the number of points, just double them up. And yeah, it's still pretty bad. We get a little bit more, but it's just junk. So then we add more points. And I have a feeling this one's going to be pretty good. And it is. You can even see the exact solution behind it. You're basically capturing most of the little blips and all the little oscillations, right? But we had to go to a pretty finely resolved simulation to do that. And of course, in 3 dimensions, which is where fluids live, you have to do this kind of mesh refinement in all the dimensions. And I know some of you are thinking that you can do that cleverly, and you're right. That's an active area of research. How do you refine in all the dimensions? But for now, the takeaway point is that it's challenging to capture all the scales. And to show you a function that I have no idea what it looks like, this is from a turbulent simulation. I have the heat transport as a function of time. The turbulence has reached a statistically steady state at this point. And you can see that the signal is turbulent. It's a big mess. Lots of wiggles all over the place. And in order to capture all the scales in this simulation, we actually used an adaptive time integrator, so that the time step is actually changing based on what the physics is doing at that point. And so we're able to capture all the wiggles that we possibly need. That might not be a good idea because it takes forever to run this thing. OK, so that's my big, broad introduction. So fluids are everywhere. We want to understand fluid behavior because this allows us to make scientific predictions and design engineering systems. And we want to understand it because we're curious, because fluids are awesome, and who wouldn't want to study them? The mathematical description is challenging for analytical techniques so far. I originally said that it defies analytical techniques, but I didn't want to offend anyone because there have been profound developments in analytical approaches to solving the Navier-Stokes equations, but there's still no general approach to dealing with those equations. So that's what that means. It's very challenging. And of course, the numerical methods are needed, but these also struggle, which hopefully I've given you some intuition for why. We have multiscale phenomena. We need to resolve our grid. We just can't solve everything. All right, so let's talk about turbulence. So people have tried to define turbulence, and there's no real great consensus on what it is. Disordered fluid flow, high-dimensional chaos is a fun one, although that route didn't really go anywhere. And multiscale phenomenon, which is a pretty vague but good description of it. So we go back to this classic picture on the left here by good old Leonardo da Vinci. I guess he was somewhere one day and he noticed some water entering into a basin and he sketched this. And I mean, that guy was brilliant because he captured a lot of the motions here. He saw that you get this big vortex swirling around in the basin. That's a large scale. And then he saw that there were all these little vortices, little eddies shooting off into smaller and smaller scales. And he observed that in the middle, it's just a big jumbled mess of lots and lots of scales. Really cool thing that he did there. And on the right here, this is from a book, Van Dyke's Album of Fluid Motion. You should all get it. It's really nice. It's from the 70s, but it doesn't have just turbulence in it. It has lots of cool pictures of fluid mechanics, shock waves, low Reynolds number flows, all sorts of things. What you're seeing here is a fluid flow coming from left to right, and it's kind of going over this wavy wall. And far away from the wall, the fluid is slowly streaming, or not slowly, but it's smoothly streaming in. But as it gets to the wall, it separates, and you get all these complicated motions. This is from an actual turbulence experiment. It wasn't a sketch by Da Vinci. This is, well, Da Vinci was gone by then, but it's not a sketch. It's an actual turbulent motion from an experiment. All right, so let's go a little deeper now and talk about hydrodynamic turbulence and what's going on a little bit more. So on the left here is a picture of, kind of a classic picture by now, of an array of wind turbines in some kind of mist. And there's a fluid flow from the bottom left corner up to the top right corner. And as this fluid kind of interacts with the wind turbines, you get these large poofs that are coming out, right? The fluid kind of becomes unstable in some way. So notice that this first large poof that I'm pointing out right behind that first turbine is big. It's about the size of the turbine, right? That's the largest scale structure that we have in the turbulence. And beyond that, you start seeing that there's a breakdown, right? The big poof starts to break into smaller poofs and so on. And eventually, there's just all sorts of scales that are interacting. And the idea here is captured on the right by this energy spectrum. This is a cornerstone of turbulence theory. So in energy spectrum, we've got the energy contained in a scale k. So this is a plot of energy as a function of wave number k. Wave number is like 1 over length. So the really large wave numbers are on the far right. Those are the smallest scales. And the really small wave numbers are the biggest scales. They're on the left. And most of the energy is in the big scales. That's like the big poof behind the turbine. But that turbine's the turbine's not unstable. The poof is unstable, and it breaks up into smaller scales, and now the energy that was in that big structure is now in the smaller scales. Those things become unstable, and they break up, and they pass the energy to smaller scales in a cascade. And this idea goes back to Richardson, I think, in like 1922, and then Kolmogorov in 1941 was able to mathematically formulate this a little bit, kind of through dimensional analysis, by the way. He didn't use the PDEs so much. And what he's found is that in a certain region, between the largest scales and the smallest scales, in that region, the energy is transferring between the scales like k to the minus 5/3. And this is still one of the kind of hallmarks of turbulence theory. It's been updated over the years. It's found to be kind of maybe invalid for some flows, but at least in hydrodynamic flows, it's thought to be universal to all turbulence in that region. So that's kind of a big deal. And there was a lot of hope in the 40s that this would lead somewhere, and I'm still presenting it now. So, all right. So it's often stated that turbulence is the last unsolved problem in classical physics. Why Why is turbulence hard? System of nonlinear PDEs, so it's analytically intractable. Experiments are challenging due to the multiscale nature. You need to have really high resolution apparatus to be able to measure these things. Numerical simulations can't achieve parameters found in nature in general. And there's non-intuitive behavior. So turbulence is actually like non-local phenomena, non-local effects going on. Statistics aren't Gaussian, so things just kind of are hard for our human mind to just see the light. You might have heard of the anecdote that, and I don't really know who this goes back to anymore, but it's usually attributed to Heisenberg, who worked in quantum mechanics, and turbulence, by the way. And apparently someone said, what are you going to ask God when you die? And Heisenberg said, basically, is there a solution to turbulence? All right. So we want to solve this thing numerically. So I'm going to show you what that's called. If we do this in the fluids world, we call that direct numerical simulation. That means we're going to solve all the scales, everything, all the time scales, all the spatial scales. So here's the energy spectrum. This is counting for space. So what that means is you're going to resolve all the littlest, tiniest scales, which are like the length scales near viscosity. Okay? And you have to resolve the largest scales, which are like the size of that turbine. So this could be like a 6-order magnitude separation in scales. And there's no clear scale separation here. It's not like you can just kind of chop things off and ignore the smallest stuff. There's no clear scale separation. That's a big problem. If you try to do this simulation, the cost scales like about Reynolds number cubed for a 3D isotropic turbulence, which is like the simplest type of turbulence. And the Reynolds number is, I haven't introduced it yet, but it's the ratio of inertial forces to viscous forces. And that just means the inertial forces are the things that are moving things around, right? That's the nonlinear term. That's the transporting the heat or whatever the case is. And the viscous forces are the things that are kind of just sucking energy out. That's where viscosity is. In turbulence, the Reynolds number is really high. And so your inertial forces dominate over the viscous forces. So I have this cute little example just to illustrate some things. This is, suppose you want to simulate things over a Boeing 777 fuselage. It's actually not such a practical example because we don't really need to do that, but it's relatable because you've all flown in these things. So you want to try and resolve all the scales maybe in the wake and all around the wings and everything around this Boeing. It's not isotropic turbulence, but let's just pretend it is because we can actually do that calculation. The Reynolds number is about 10 to the 8th. Around this thing if it's flying at Mach 0.7, which is not incompressible, but let's pretend it is. And we are going to assume the next generation of computers is here. This is like the exascale machines. And so that's like 10 to the 18th floating point operations per second. And so those are big machines. They're not here yet. A simulation running on that thing would take about 5 years of continuous running. That's just totally back of the envelope. And actually, it's going to take longer than that because I made a huge amount of assumptions here. And not to mention that people are going to hate you for taking up all the resources in an exascale machine, and they're not going to give you access to the whole machine. Not just to mention that, but this is a huge power consumption because these machines might consume as much energy as a city, right? So it's just not going to happen. Probably, I don't even know if it's going to happen in the lifetime of my grandchildren. Fortunately, planes do fly, and they're safe. And they're not using direct numerical simulations to resolve everything around here, right? Because engineers and scientists were really interested, well, I should say maybe more engineers are really interested in the large scale behavior, right? You want to figure out what's the average lift over this wing, right? Or what's the fuel consumption, or what's the drag, right? And this can be determined to a pretty good accuracy by just looking at the average kind of quantities. You don't need to know all the little micro details about what's going on. So what do people do? Well, there's a few classical approaches. I'm going to talk about two. There's large eddy simulation. And the idea here is that you go to your energy spectrum and you just truncate the modes that are bigger than this cutoff frequency, Kc. So you're going to numerically solve for the largest eddies in the system. You're going to solve for them exactly. And then you have to come up with some mathematical model for the smallest scales. That's like turbulence modeling. Because like I said, there's no scale separation, so you can't just ignore these things. They're still there. And you have to take into account their effects at the very least, even if you don't care exactly what they are. Another nice way to do things goes back about 150 years or so to the Reynolds average Navier-Stokes equations. And the idea here is that you see this kind of light blue line that's really high frequency, lots of things going on. So what you don't care about the high frequency components so much. So you're going to average them out in some way. And you're just going to try and figure out what this big fat red line is doing. And those are like more slowly varying things. And that'll be able to give you, hopefully the drag force or that kind of thing. So I'm going to focus mostly on the RAND stuff today, but I just want to, this is sort of a bifurcation point in the talk. So before I bifurcate, I wanted to show you that this lower left corner plot here is some work on thermal convection. This is a direct numerical simulation that we were doing to try and figure out what the optimal heat transport would look like in this kind of a system. This is 2 plates, cold one on the top, a hot one on the bottom, and this is the kind of structure, the temperature field looks like that optimizes heat transport. That's a full DNS simulation. It's actually an optimization problem, and it's really expensive to do. But you get really beautiful structures out of that thing. The question is, are they actually found in turbulence? And then on the right here is a simulation used from magnetohydrodynamics. Now we allow the fluid to be electrically conducting. And the blue lines, the really, really disordered ones, that's the velocity field. And the red and orange lines are a magnetic field. And they're interacting with each other. And that's from a large eddy simulation. That's not a direct numerical simulation. And we were able to capture a bunch of the scales. OK, but today's story is about RANDs. So I'm going to move into that now. So now we're going to get to actually see some equations, finally. So I know you've been waiting. So we're going to work with an incompressible Newtonian fluid, and it's got conservation of momentum and conservation of mass. Conservation of momentum is this kind of long equation on the left. You have the first term here is the rate of change of the velocity field, u, which is a vector as a function of time, it's a 3-dimensional vector field. Then you have your convection term, which is the tensor outer product of the velocity field, divergence of that. And then on the right-hand side, you have your stress tensor, which has an isotropic part, which is the pressure, and a viscous stress tensor, which we assume it's Newtonian, so we just have a viscosity mu times these gradients in the velocity field. And then you allow for a body force, F, which could be gravity, buoyancy, electromagnetics, nuclear reactions. I don't know what you want to put in there, but it's going to be 0 for this talk. And on the right here, you have conservation of mass. It's an incompressible fluid, so divergence of u is equal to 0. Now, you introduce a Reynolds decomposition. U is equal to u bar plus u prime, where the u bars are some smooth field. You can sort of think of it like an average. And the u primes are fluctuations about that smooth field. You put those into the momentum equation, you turn the crank, and out pops this equation, which looks kind of nice and benign. It doesn't look any different. You have the u bars now, because that's what you're trying to find. And then, unfortunately, you do get this one little difference, which is the average of a second-order structure. Right? It's the covariance of these fluctuations. Pavlos. I said it's 0. Yeah. So, OK. So it turns out that people have been worried about this right term for about 150 years now. And the goal is to find just u bar, the slowly varying thing. And the main challenge that these things called the Reynolds stresses are unknown. We don't know what they are, but they're important because they capture all the stuff that we neglected, right? So we need to find out a way of modeling their effects. In case you're not familiar with the notation of this tensor outer product, I put it in here. U dyadic V is equal to UV transpose. And then it's just this matrix form here. So just to make you feel better, in case you haven't seen it. All right, so I'm not going to give a history of all the different types of turbulence models people have tried to develop because we would be here for a long, long time. So I'm going to introduce a linear turbulent viscosity model. So the Reynolds stress tensor enters the RANDS equation similarly to the viscous stress tensor. And all I mean by that is that it comes in through a divergence term, right? Divergence of some stress. So there's the Reynolds stresses. That's why they're called stresses. Just an analogy there. And so Boussinesq, back in 1877, said that the Reynolds stress tensor is proportional to the mean rate of strain tensor. So you can think of this thing on the left as the Reynolds stress tensor, and it's proportional to these gradients in the velocity field, the u bars, gradient of u bar. And the proportionality is through this nu t, which is a turbulent viscosity. Now, that's not a crazy idea, actually. It turns out it's totally wrong for turbulence, but in 1877, that's actually a great place to start. The idea here is that from the molecular theory of gases, viscosity arises because you have molecules that are bumping into each other and exchanging momentum. Well, why don't we think of turbulence as a whole bunch of eddies that are bumping into each other and exchanging momentum. And that's going to induce this turbulent viscosity. It's a great analogy. It's just wrong, unfortunately. So once you plug that in, you get the Rand's equations, which they look great. Now we just have U bars here. And everything's closed up, right? We don't have any more U primes hanging out. Of course, you do have the question of what is nu t. We've sort of hid a bunch of stuff inside of there. And over the years, people have come up with many, many models. Your classical mixing length models and some refinements on that, like the K epsilon model, K omega model, and the list goes on and on and on. So if we knew what the nu t was, then everything would be closed. And if this assumption was good, then we could proceed. Engineers still use this form. They've made adjustments, but this is pretty quick to solve. Right? And if you're trying to do a simulation around an airplane wing to figure out what the lift over it is, and you only care about the U bars, and you need to do like many simulations a day because you're doing some design problem, then why not just use this thing if the nu t has been calibrated very carefully to that airplane wing, right? That's not a bad idea. It's sort of unsatisfying from a physics point of view, but it'll make you money. So, all right. So what you can do, I'm actually not going to talk about what nu t is. I'm going to depart from that for a moment. And I'm going to talk about a more general model. So I just introduced a linear model. It's linear because you see there's linear in the velocity gradients, right? Just have grad u's. You don't have grad u's squared or anything like that. So in 1975, Stephen Pope introduced a nonlinear model, the most general nonlinear model that depends only on velocity gradients, local velocity gradients. And so you have this nonlinear model is a linear combination of some basis tensors. The t's are known, and the g's are the coefficients. We don't know what those are. Now, just to show you that things aren't crazy here, if you expand this series, A is equal to G1 times S, where S is just the first t, and then you have a bunch of other terms. That thing looks just like the linear eddy viscosity model. So G1 is somehow like nu t. Some advantages of this form, it potentially captures more of the turbulence physics because it's nonlinear. Why not? But actually, it's able to capture like mean streamline curvature and this kind of stuff. It preserves symmetry of the Reynolds stress tensor, which it's symmetric. It has to be able to preserve that symmetry. And this model has Galilean invariance built in, which basically just means that if you're moving in like the fluid equations are unchanged in any inertial reference frame, right? So if you're hanging out here, I'm not moving. The fluid equations are the same, but if I'm translating at a constant velocity in that reference frame, the fluid equations are the same. That's kind of important. All right, so Gn is a very complicated function, and Pope says in his 1975 paper, in like deeply embedded in that paper, he says, in parentheses, he says, for general three-dimensional turbulent flows, this is completely useless. So maybe he was worried it wouldn't get published if he did put it up front. So, but now we say, well, Gn is a very complicated function, and there's sort of this renaissance now in some algorithms to learn complicated functions, so maybe we can see if those new algorithms work. So that brings us into this whole business of machine learning. So I'm not going to give an overview of machine learning. I'm just going to say that in 2016, Ling and her collaborators proposed to learn these Gs through a neural network. The idea there is that neural networks are universal function approximators, so G is a high-dimensional complicated function, and so maybe a neural network will be able to learn what those Gs should be. So the way this is sort of a workflow of how this thing works. So you have some inputs which depend on the velocity gradients. Comes into your run-of-the-mill feed-forward, fully connected neural network. That's the MLP. That thing does what it does, and it pops out the Gs. And then you form this linear combination, Gn, Tn, to get the As. And then you have an A, and you compare that A to the A coming from some data, like from a direct numerical simulation, if you happen to have that data. And then that loss, depending on how well they compare, you go back and you update the weights in the neural network, and you proceed, right? And then hopefully you get a good A out. Now, it would be very desirable to embed physics into the network, and that's what motivated this form. Julia said that she'd like to embed Galilean invariance in, and this nice tensor basis has Galilean invariance just mathematically as part of it. So that is how she was able to embed Galilean invariance into her network. But it would be really cool if we could embed other laws into this thing, like conservation laws, and could we actually embed it directly into the network, right, instead of doing this kind of ad hoc thing at the end. And so today I'm not going to get into that. I'm just going to talk about this network. So there's a master student named Ray Fung in our IACS program, and she's been working on this network for the channel flow test problem. So Julia, in her original work, she did channel flow, she did backward-facing steps, she got really nice results. And so Ray was trying to figure out, how does this thing actually perform? Right? Like, what's kind of going on under the hood? So she was looking at this three-dimensional channel flow. Y is the y direction from the bottom to the top of this channel. These black lines represent two parallel plates. They're at y equals negative h and positive h. Z is into the page, and x is in from left to right. And that's the direction that your fluid is flowing. Now, this is a very simple problem in that it's statistically stationary and one-dimensional. The average fields are. And so u bar is just a function of, it's just u bar, the x direction, as a function of y. And the v bars and w bars are 0. Now, even though I just said it's simple, it's not so simple because it's turbulence. So the Reynolds stress tensor for this guy, it looks like this, where you have lots more zeros. You have these 3 diagonal components, and then you have 1 off-diagonal component because of the symmetries. And if you write the Brand's equations for this system and process them up a little bit, you see that the gradient of the velocity field, the u bar, the thing you're trying to find, is really just driven by the u prime v prime component of the Reynolds stress tensor. Right? So if you wanted to predict the u bars, then if you know what the u prime v prime is, then you get your u bars. You don't really care what the other 3 components are here. All right? Now, if you wanted higher statistics of the u's, then you would probably need the diagonal terms. But just for getting the average velocity out, it just depends on the single off-diagonal component. So Ray went through and she ran Julia's network. She trained it on a DNS flow from M.K. Lee and Bob Moser and UT Austin. And what I'm plotting here is the u prime v prime component from the Reynolds stress as a function of distance from the wall. And I know what you're thinking, how can you be 1,000 away from the wall? And it's because it's a dimensionless unit where 1,000 here represents the middle of a channel and 0 on the left represents the lower wall. Now, the blue thick line, which you may or may not be able to see underneath everything, is the DNS data. That's the truth, right? Direct numerical simulation is all the information you ever want. And the dashed orange line is a prediction from a linear eddy viscosity model, which is completely wrong in the near wall region. And it does OK in the bulk, but it's known that this thing doesn't perform well. And the tensor basis neural network is the red dashed line. And we see that it's pretty close to the DNS, looking pretty good. And if you just do your standard feed-forward network, the results are better than the linear model, but it's kind of just doing its own thing. I don't know what it's doing. It's not doing the right thing, right? The results are kind of off. All right. Oh, that was at a Reynolds number of 20,000, by the way. So the next question is, OK, we got some promising results. Can you predict the Reynolds stress tensor? So train your network on a specific, like Reynolds number 20,000, and now predict the Reynolds stress tensor at like 125,000, right? Something it's never seen before. The physics are probably different flow structures. All sorts of things are going on in there. And so Ray trained this thing on a Reynolds number 20,000. This is plotting the u prime v prime component again as a function of the distance away from the wall. The thick blue line is the DNS solution. The red dashed line is just the prediction from the tensor basis neural network, just run-of-the-mill tensor basis network. And the blue line is what we call this transfer learning approach. The idea here is that you just embed a little bit of information from the DNS simulation into your neural network. You retrain just a little bit, and maybe it'll have enough information to improve the results. And we see that it still doesn't do great near the wall, but it actually does improve as we approach the center of the channel. And so you might say, well, the red line is just about as good. So if we look at another component of the Reynolds stress tensor, we see that the network is actually trying to adjust different components of the Reynolds stress tensor. This is the first entry, the u prime component, also as a function of the wall, predicted on 125,000 Reynolds number. It looks different because it's a different component. The DNS is the solid black or blue line again. And we see that with the transfer learning, the results have improved in sort of this, not near wall region, not bulk region, but kind of in this middle of the plot here. The results are pretty awful near the center of the channel, and we know why that is. That's because of the symmetries of the channel flow and because of the mathematical structure of the tensor basis, so we don't need to get into that now. That's actually not a deficiency of the neural network, and Ray was actually able to show that the neural network is trying to do the right thing. It just can't because of the mathematical limitation of the form we put in. All right, so I'm going to just conclude a little bit here now. So Ling, Julia, proposed a new network to learn the Reynolds stress tensor, and the network respected some physical constraints like Galilean invariance. The predictions of the Reynolds stresses are encouraging, both in Julia's work and in Ray's more detailed study of this stuff. And she also extended this to train on lower Reynolds number and predict on a higher Reynolds number. And this is work in progress, where she's trying to use transfer learning techniques to try and understand how we can improve the predictions here. There's lots of other things that can be done. I've just listed a few that came to mind. Really, number one here I have, can we embed more physics directly into the neural network? Right? So like time reversal symmetries, conservation laws, or what have you. Although Navier-Stokes isn't time reversal, but we'll find another PDE. Two, can a neural network compete with classical approaches in solving ODEs and PDEs? So we could probably use this thing to solve these equations. And how does it actually compare from like an analysis point of view? Right? What are the convergence rates and that sort of thing? How do you account for non-local effects? I mentioned turbulence is a non-local phenomenon. This whole thing that I just showed you totally depends on local representation. How do we account for non-localities in time and space? And then another thing that's just kind of in the back of the mind, can unsupervised techniques provide insights into turbulence? Because DNS simulations are extremely expensive, and we don't really have access to the data necessarily, right? So maybe some kind of unsupervised technique will shed some light in some direction. All right, so I'm just about done. I just want to summarize so you take something away. So fluids are everywhere, from astrophysics to biology to geophysics. They exhibit a range of behaviors, and understanding their behavior allows us to kind of move forward in science and engineering. Turbulence is really challenging because analytical, experimental, and computational approaches all struggle with this problem. We can find reduced models that express the essential physics, but coming up with good reduced models often introduces other problems. And lately, machine learning has been used to try and augment these models and just to see if it's able to help us get a little bit better models in this arena. Okay, thank you. Do we have time for questions?
Yeah.
Questions? Yeah.
What do you mean you're going to use a neural network to solve a PDE? What do you mean by that?
So I can write something down for you later, but you can think of your PDE as some kind of operator that equals 0. And what you're trying to do is you're trying to find the function that satisfies that operator. So you're going to use the neural network to approximate a function that satisfies that operator. But yeah, we can go more into it later if you want. Other questions? Yeah. Oh, that's a great question. I think there's a lot of difficulties, and I don't think we've even encountered all of them yet. But I mean, what's the right way to do it, first of all, right? Like some obvious things come to mind, like what Julia did was a nice step in the right direction. But that wasn't directly embedding things into the neural network. You could imagine doing something like a penalization or regularization term, but that somehow is a little unsatisfying too, because it's kind of ad hoc, right? And so then you start wondering, like, what does it mean to actually embed it inside the network? So you start thinking about, like, can you come up with constraints on weights, or I'm not exactly sure how it's going to manifest. Yeah. Yeah.
Two-dimensional turbulence, you have these vortices and they're sort of like in 3 dimensions, these things begin to go.
Yeah.
So the question is, are these techniques applied to two-dimensional turbulence? Would they be giving you some intuition of how they
Yeah, that's kind of a deep question, because there are fundamental differences, as you pointed out, between 2-dimensional and 3-dimensional turbulence. for example, one of the most prominent differences is that I've just been talking about this energy cascade. The energy is transferred from large to small scales. So you think about vortices breaking up. But in two-dimensional turbulence, actually you can have an inverse cascade from small scales to large scales. So two vortices might come together and make a big vortex, right? So it might be that some insights are gained by looking at two-dimensional turbulence, but I don't know exactly how it's going to generalize to three-dimensional turbulence.
I mean, that's the question. The question is, are these techniques applicable to two dimensions, which are much easier to analyze mathematically?
Yeah.
And then the question is, why do they blow up?
Okay. Well, so, I mean, they are applicable to two dimensions. So these eddy viscosity models and the model that I showed you here, Pope analyzed it for a two-dimensional problem, and it works fine. So yeah, the same techniques are applied. The physics are slightly different. So actually, it's kind of just as I could talk about this for a while, but one of the cool things is, you know, I talk about this eddy viscosity, which is just going to dissipate energy, kind of like viscosity does. But in 2D turbulence, you don't want that. You actually want your eddy viscosity to be negative sometimes, so it can pass energy back up, right? But I think these models, like you're not necessarily directly imposing any constraints on the coefficients. And so the turbulence model for if you had 2D data, I mean, the neural network model, the machine learning model, if you had the data, as long as you don't require you put constraints on the coefficients, it should allow them to be negative or whatever they want to be. There's no constraint there. Pavlos?
Go to slide 29.
Okay.
Yeah. So the black line is the DNS, right?
Yeah.
And the red one or the blue one is our network.
Yeah.
So do you know where our training points are? In any one of those, do we have training points where the errors are, or we don't?
We have them, right, Ray? We just didn't put them on here?
Yeah, I know
Yeah.
she has it, but
Yeah.
do you have an idea if we have, go to the next one. So do we have points around 5,000?
Yeah.
Are these uniformly spread, the training points?
No. The distribution is a DNS. Distribution of the DNS. So since DNS is not uniform.
Yeah. Have you done any analysis where the error is higher versus the training points?
So,
Wondering if the error appears where we don't have training points, you just fit it where the training points are.
yeah.
Because they may be overfitting around the training.
Yeah, so we started to look into that. We haven't finished the conclusion, but that goes to the question of, like, in here, you know, it's nice and smooth in the middle here, but I didn't show you what's happening in the boundary layer close to the wall, and that matters a lot. And
We
so
don't have training points there.
I don't think we do have. I don't think we have enough. That's my point. So one of the things we're looking at is maybe she can take some points from the middle,
So
put them
actually
in.
the question is, how do you draw that black line? Why do we have 2 points, right?
Well, she has what, almost 1,000 points there from the DNS.
But it looks like a continuous.
Oh yeah. I understand. So if you do the
Are you smoothing it, or?
yeah, basically, yeah. So I can tell you more about that. Yeah, yeah. Oh, yeah, you're right. Totally right. Okay, yeah.
Talked about using unsupervised learning
Yeah.
as sort of the next approach to helping this process. Can you elaborate a little bit, like what would unsupervised learning do? What are some of the unsupervised learning methods that could be applied?
So this is a really fun question. I think about it while I'm walking my dog. See, I had to talk about my dog. So, like, what do you hope to gain from using unsupervised methods? Because I'm pretty confident that just throwing a neural network and hoping to learn turbulence isn't going to work, because that's going to amount to doing a DNS, but now on a neural network. And it's going to be the biggest neural network of all time, and you can't solve it. It's not going to be possible. So, okay, we can have a fight later, I guess. He doesn't agree, but I'm pretty sure about that. Now, one of the things you could do, though, what I would be interested in is turbulence is, one thing we've noticed is it has these coherent structures in it. And so one of the things I've been kind of mulling around is, could you use an unsupervised technique to learn the coherent structures And then maybe you can use those coherent structures as some kind of physics basis for your network, right? I mean, for your turbulence modeling or your turbulence, right? And that physics basis idea is not new to turbulence. People have been trying to do that for a while. But to try and find some kind of subspace where these, like finite dimensional subspace where these coherent structures live might not be very easy or obvious. One thing that comes to mind is like these variational autoencoders stuff that people like to use to try and take your, reduce things down to some finite subspace where you find some features, right? Reduce feature set, and then to expand that back out. But I haven't tried any of these things yet for turbulence, but those are some of the things I'm thinking about. Yeah. Neural network focused, right? So there could be other machine learning techniques that aren't neural network either. But I haven't thought about those either. Yeah, yeah.
All right.
All right, thank you.